Welcome back. In this video we're going to do a couple of example problems of splitting fractions just to try and refresh your memory and give you a couple of new techniques. And I talked about this in the overview, so if you want to go back and look at that you can, but we'll just do a quick review. If I have a integral with a fraction, right, very simple stuff, right, I can split this up into two integrals. But I can break up the integral at this point where there's addition. If I had a larger integral, you know, something like this, right, all over some common denominator, let's go 5, right, I could split that up as x over 5 plus 3 over 5 plus x squared over 5. You know, if this becomes a 5 plus x, then each one of these is going to get a plus x. You get the general gist of splitting up fractions. So the first thing I think of when I look at this integral is I do not want fractional exponents, right? This 5/2, 3/2, and this 1/2, it doesn't look good. It's similar to negative exponents. You don't want negative exponents. So I'm just going to multiply by 1, right, to get rid of that those fractional exponents. I'm going to do 1/2, right, over x to the 1/2. And remember, this doesn't change the value of the integral. We're still multiplying by 1. X to the 1/2 divided by x to the 1/2 is still just 1. And so we get our new integral written as, right, when we increase this power by half, it goes to 6 over 2, which is 3, 2 over 2, which is 1, and 4 over 2, which is 2. And then this fraction can be split up with the standard splitting fractions. Now we have a very simple integral that can be rewritten as the integral of x, because 3 minus 2 is x to the 1, right? When you divide, you can subtract exponentials, and we will have, and now we have a very, very simple integral, right? We can integrate as x squared over 2 minus ln the absolute value of x, because the integral of 1 over x is just ln absolute value of x, and our integral is completely solved. The next integral that we're going to solve is going to be a trigonometric integral, just so you can kind of gain an understanding of, you know, how trigonometric functions can also be split. This trigonometric function, right, we're just going to split it right where the plus is, so we're going to get the integral of sine x over cosine squared x plus the integral of tangent x over cosine squared x, right? And I'm, you know, not remembering to put these dx's here because I'm a little bit lazy, but I think it would help. And now let's just do the first one, right? So we have the integral of sine x over cosine squared x dx, and what stands out to me is that we have a single sine x, right, in the numerator, and that would make for a very convenient u substitution of cosine x, right? So that the derivative with respect to u is going to be negative sine x dx. And in order to sub in our du, we have to get rid of this dx, we have to get rid of this sine x, and we have to multiply by negative 1 over negative 1, right? Because we have a negative symbol right here, so that that negative gets canceled out. And now we're left with 1 over negative 1, which is just negative 1 over u squared. And this is just equal to negative times negative u to the negative 1, right? This 1 over u2 can be rewritten as u to the negative 2 power. And when you increase by 1, you're going to get negative 1. And you're going to bring down that negative 1 right here, right? And a negative times a negative makes a positive. So you just get 1 over u. You get u to the negative 1, right? These cancel out. And you're left with u to the negative 1, which is 1 over u. And we sub back in our u, and we get 1 over cosine x. So that's just the first integral right here. Now we're going to do the second integral. Now this integral stands out to me, right? I see 1 over cosine squared x, and we know that 1 over cosine is just secant x, so 1 over cosine squared x is going to be secant squared x. So this second integral can be rewritten as tan x secant squared x dx, right? And if we do u substitution, right, this is a very, very common u substitution. You should remember this. If you just see a tan x and a secant squared x, you need to use u for tan x and the du as secant squared x dx, right? This is a standard derivative that you have to memorize. You know, the derivative of tangent x is secant squared x, but we have this very simple u substitution, so now we can rewrite that integral as u du, right? Because we got our secant squared x, and that dx cancels to give us du, and our tangent x is just u, and so the integral is going to be u squared over 2, which is, when we sub back in our u, we get tangent squared x over 2. So we determined that the derivative of this function is 1 over cosine x, and the derivative of this function is tangent squared x over 2, and that is our final integral. We've solved it. Now we're going to do one last one. Very easy. 2 minus 3x over the square root of 1 minus x squared. And we see this minus or plus here, it just goes straight to splitting the fractions, so we're going to get the integral of 2 over the square root of 1 minus x squared, and we're going to get minus 3x over square root of 1 minus x squared. So let's just solve this first integral. I'm going to use the constant multiplier rule to take out that 2 and rewrite it as 2 times the integral of 1 over 1 minus x squared. And I'm doing this because I recognize that this form, right, this is just the derivative of arcsine. So this entire integral can just be rewritten as 2 arcsine of x, right? The general form of arcsine, just as a reminder, and you should memorize this, is 1 over the square root of a squared minus x squared, right? And whenever you see this, you know that it's going to be equal to the integral is going to be equal to the arcsine of x over a. And this is a standard integral, right? If you see arcsine of x over a, the derivative is going to be that, and the integral is going to be that, right? You just have to memorize that one. And so in this example up here, we see 1 over 1 minus x squared, which means our a is just going to be 1, and our x is going to be x. And so we can rewrite this integral as 2 times the arcsine of x. That's our first integral, very straightforward, very easy. And let's do our second integral, which is just 3x over the square root of 1 minus x squared dx. Now the first thing that stands out to me is that there's a very convenient u substitution that can be done here, which is the x squared, right? So I'm going to rewrite this 1 minus x squared as negative x squared plus 1, right? You have negative x squared, you have a positive 1, you can add them together. And then I'm going to take its derivative, and we're going to get negative 2x dx. What we see up here is a 3, not a 2. Okay, so in order to solve our integral, right, we need to multiply by 1, which we're going to do negative 2 over negative 2, right? And we're going to have a 3x over square root of 1 minus x squared dx. And this dx, right, it's going to cancel. That x is going to cancel, and that negative 2 is going to cancel and give us a du. And so we're going to be left with negative 3/2 the integral of 1 over the square root of u du, right? We get that 3 from that one right there. We just pulled it out with the constant multiplier rule. Dividing by negative half gives us negative 3/2, and we multiply it by 1 over the square root of u. The integral, right, we're just going to kind of ignore this negative 3/2 right now and focus on the integral of 1 over the square root of u, right? This 1 over square root u can be rewritten as u to the negative 1/2, right? Because that square root u is just u to the 1/2, and since it's in the denominator, if we want to move it to the top, we've got to make it a negative exponent. And if we're integrating, we add 1, right? So we're going to get u to the 1/2. We divide by that new power, which is just 1/2. And any number divided by some fraction, all you have to do is multiply by the reciprocal of that fraction. So we're basically going to get our integral is just u to the 1/2 times 2 over 1, right? That's the reciprocal of 1/2, which gives us 2u to the 1/2, okay? And now we need to multiply by that outside negative fraction that we had created. And in order to multiply, when we multiply by it, right, we're going to get negative 3u to the 1/2. Now we're going to go back and fetch our u, which we said our u was x squared plus 1, right? And we're going to plug it back in. And we're going to get our final integral for this one is negative 3 negative x squared plus 1, right, to the 1/2. Okay? Our final integral is 2 arcsine of x, right? That's the first integral, minus negative, so it's just going to be a plus, minus 3 square root 1 minus x squared, right? This is the same thing. I just used the 1/2 power. I wrote it as a square root, and I rearranged this negative x squared plus 1 as negative 1 minus x squared, right? And that's our final integral, and this problem has been solved.